Hello and welcome to Unit 1 of Fluid Mechanics. Today we're going to talk about the history of fluid mechanics. So this module has 10 units. The first unit is the subject of today's lecture, which is the history of fluid mechanics. And we're going to have a look at the history of the subject, the people, some of the great academics that have contributed to this field, and look at some of the research work that they've undertaken, which has led us to the position we're in today, where we have the mathematical theory and some of the concepts we can apply to the subject of civil engineering, hydraulics, and water engineering. So in this lesson, I'm going to define the subject of fluid mechanics. I'm going to provide an overview of the ancient solutions to moving water for consumption and irrigation, identify the most important academic contributors to the field, and discuss some of these significant contributions. The picture you see here is of John Cornelius Hobart. He was an aerospace engineer credited with leading the team behind the Lunar Orbit Rendezvous mission mode, a concept that was used to successfully land humans on the moon and return them to the Earth. So why have I got a rocket scientist here? Well, fluid mechanics is a subject that you can apply to the subject of rocket science. So, although this module, some parts of it may prove to be relatively simple, some of it becomes a bit complex. And ultimately, this is a subject which contributes to rocket science. So by the end of this unit, you should be able to explain the ancient engineering approaches to managing water. You should be able to describe the key contributors to the field of fluid mechanics, identify the key experiments that influenced fluid mechanics theory, and explain the key historical scientific experiments and their influence on current engineering practice. So the science of fluid flow can be classified into hydraulics, which developed from experimental studies, and hydrodynamics, which developed through theoretical studies. In recent years, the two subjects have merged into a single discipline that we know of today as fluid mechanics, and that's going to be the topic of this module. Fluid mechanics covers statics, kinematics, and the dynamics of fluids. Hydraulics developed as an empirical science with practical techniques beginning in prehistorical times. The irrigation of crops and the transportation of food and materials posed the earliest problems associated with hydraulics. We've discovered ancient irrigation channels in Egypt and Mesopotamia that were estimated to have been constructed in as early as 4000 BC. Jerusalem saw early examples of reservoirs and storage and masonry channels to convey water to the city. The Romans also constructed aqueducts throughout their empire. The civilization of ancient Mesopotamia grew up along the banks of the two great rivers, the Euphrates and the Tigris. They relied upon these rivers to provide drinking water, agricultural irrigation, and major transportation routes. What they did was learn how to harness water. Farmers diverted from canals into irrigation ditches. They constructed a series of waterways and ditches from the rivers to their fields, and this created a reliable water source for farming. The crops fed the population, and the farmers were able to trade the excess produce such as onions, garlic, apples, figs, grapes, and pomegranates. The Romans constructed considerable infrastructure. The Romans constructed a broad range of water infrastructure, and here you can see an artist's impression of two of the great aqueducts in the Roman Empire. The diagram at the bottom shows an intake behind a dam and a reservoir with inspection shafts, settling tanks, covered channels constructed on masonry arch aqueducts, distribution tanks, which eventually led to the cities that they constructed. One of the greatest Roman civil engineers was Sextus Julius Frontinus, an author, soldier, and senator of the late 1st century AD. In 97, he was appointed Curator Aquarum, supervisor of the aqueducts, by the Emperor Nerva, an office only conferred upon persons of very high standing. best known to the post-classical world as an author of technical treatises such as De Aqueducta, dealing with the aqueducts of Rome. This publication presented a history and description of the water supply of Rome, including the laws relating to its use and maintenance. It provided details on the history, the size, the discharge rates of all the 9 aqueducts of Rome. He described the quality of water delivered by each, mainly depending on their source, be it a river, a lake, or a spring. The Romans consumed a huge amount of water, in the region of 1,000 cubic meters per day, and this is comparable to present-day consumption in the city of Rome in Italy. The water was used for public use, in particular baths and for sewers. De Aqueducta provided a treatise on the aqueducts of Rome by this great civil engineer, Frontinus. They ranged from 10 to 100 kilometers long. They used inverted siphons to move water across valleys, where it was impractical to build aqueducts. The Roman legions were responsible for construction and also maintained these structures, which were unfortunately maintained often by slaves. They also constructed dams, the greatest being the Subiaco Dam, the highest in the Roman Empire, which was accidentally destroyed in 1305. So the movement of a gas or liquid, collectively called a fluid, is called a flow. And the study of this field is called fluid mechanics. The science of flow has been classified into hydraulics, which developed from experimental studies, and hydrodynamics, which developed through theoretical studies. And both have merged into this single discipline called fluid mechanics. So the next part of this lecture, we're just going to look at who's who in the subject of fluid mechanics. So the subject of fluid mechanics has seen some significant contributions over the years. And here we can see 10 of the academics and engineers that have contributed to the field. Note that we see people such as Archimedes, Newton, Bernoulli, Leibniz, Euler, Navier, Reynolds, and lastly Taylor, who's not a relative, I might add. In the following slides, I'm going to go through the significant contributions that these people have made to the subject and help you understand the significance of those contributions in relation to the subject and how we apply it in civil engineering. Now, I'm sure you've all probably heard of Leonardo da Vinci, but you're probably not aware of his studies, for example, in the behaviour of fluids as they pass through bridge piers. Here you can see one of his early sketches showing how water reacts to passing an object in a river. In this case, it was a pier associated with a bridge, which he clearly observed and recorded his observations in sketches. We also see some sketches below of how water passed by objects which were placed in a stream of flow. So Archimedes was one of the most famous mathematicians and inventors in ancient Greece. He discovered the relationship between the surface of a sphere and its circumscribing cylinder. Known for his formulation of a hydrostatic principle known as Archimedes' principle and a device for raising water, still used in developing countries, and this is known as the Archimedes screw. His real interest lied in what he called catoptrics, a branch of optics dealing with the reflection of light from mirrors, plane or curved. Archimedes has 9 extant treatises in Greek. The principal results in one of the sphere and cylinder are that the surface area of any sphere of radius r is 4 times that of its greatest circle, s equals 4 pi r squared. Furthermore, that the volume of a sphere is 2/3 that of the cylinder in which it's inscribed. The volume equals 4/3 pi r squared cubed. Archimedes was so proud of his discovery that he left instructions for his tomb to be marked with a sphere inscribed in a cylinder. So Archimedes developed the theory of buoyancy, as we can see here on the left. In the middle here we can see some of his early works, and on the right we can see the ratio of a sphere and a cylinder that he discovered. Here we can see some images of some early artist impressions of Archimedes' screws. And you can see the function of this and how it was used to lift water from possibly a river into an irrigation channel for agricultural farming. The bottom right hand side shows a Dutch town with a low loader passing through with an extremely large Archimedes screw, and this has been used as a pump to lift water from one level to another. We'll talk about the Dutch and how they maintain their water levels throughout the country and the various equipment that they use to do that in future lectures. So most of you probably have heard of Isaac Newton before, and probably in association with his work in studies of gravitational fields. Newton also considered the flow of water between two parallel plates, where he discovered the linear relationship between the stress and strain and defined this as the law of viscosity. Newton's laws of motion, the laws of thermodynamics, the principle of conservation of mass and momentum, laws of motion, equations of state relating to fluid properties, restrictions caused by boundaries, all gave rise to the available methods for the analysis of fluids that we'll use today. The theory of fluid mechanics is based on the linear constitutive equation given by Newton. This equation demonstrated perfectly the motion of water, glycerine, and many thin oils. Newton's works allowed many theories to be developed by applying these equations he discovered and defined. So Leibniz was a prominent German polymath, a mathematician and natural philosopher of the Enlightenment. He conceived the ideas of differential and integral calculus independently of Newton's developments. He also invented a mechanical calculator that you can see here below. He added automatic multiplication and division to Pascal's calculator. He first described the pinwheel calculator in 1685 and invented the Leibniz wheel used in the arithmometer. Wow, that's a bit of a word to get your mouth around. The first mass-produced mechanical calculator. He also refined the binary number system, which has become the foundation for all digital computers. Daniel Bernoulli was a Swiss mathematician and physicist, and one of the many prominent mathematicians from the Bernoulli family in Basel. He is well known for his application of mathematics to mechanics, especially fluid mechanics, and his pioneering work in probability and statistics. The Bernoulli principle states that an increase in the speed of a fluid occurs simultaneously with a decrease in static pressure or potential energy. Bernoulli published his book with this theory in 1738, and it was called Hydrodynamica. This work contained a correct analysis of water flowing from a hole in a container based upon the principle of conservation of energy. Bernoulli's principle was derived from the principle of conservation of energy, which he learned from his father, Johann Bernoulli. In steady flow, the sum of all forms of energy in a fluid along a streamline is the same at all points on that streamline. This requires the sum of the kinetic, potential, and internal energy remaining constant. Bernoulli's principle can also be derived from Newton's second law of motion. There's a simple experiment you can do to examine this principle. So if you have two balloons or ping pong balls, they have to be light, hanging from a frame, maybe about an inch apart, and if you take a straw and blow not touching the balloons or the ping pong balls, and blow in between them, what will happen is as the pressure drops, they will move towards each other. And initially, if you weren't aware of this principle, you would think intuitively that they would just move apart. So if you've got the chance, why not try and get some string, a couple of balloons, attach them to something with a bit of tape, grab yourself a straw, and try this at home. If you get a chance, make a quick video of it and share it with us. So Euler was a student with Daniel Bernoulli and studied various fluid mechanics problems in the 1700s. He described how the velocity, pressure and density of a fluid are related. His work was based on Newton's second law of motion. The equations are a set of coupled differential equations, and they can be solved for a given flow problem using methods from calculus. The integration of the equation gives Bernoulli's equation in the form of energy per unit weight of the fluid. The Euler equations neglect the effects of viscosity on the fluids. A solution of the Euler equation is therefore only an approximation to a real fluids problem. So Navier was a French engineer and physicist. He worked with Stokes and created the Navier-Stokes equation. The partial differential equation described the flow of incompressible fluids. The equation is a generalization of the equation devised by Euler. In 1821, Navier introduced the element of viscosity, friction, for the more realistic and vastly more difficult problem of viscous fluids. The British physicist and mathematician Sir George Gabriel Stokes improved on this work, although solutions were only obtained for the case of a simple two-dimensional flow. Sir George Stokes was an Anglo-Irish physicist and mathematician, born in County Sligo in Ireland. He spent all of his career at the University of Cambridge, where he was eventually the Lucasian Professor of Mathematics, and this was a post also held by Isaac Newton. Stokes was part of a trio of natural philosophers, including James Clerk Maxwell, Lord Kelvin, who all significantly contributed to the fame of the Cambridge School of Mathematical Sciences in the 19th century. His seminal contributions to the fluid mechanics subject included the Navier-Stokes equations. He also contributed to the field of physical optics with notable work on the polarization and fluorescence. His first published works were in 1842-43 and were on the steady motion of incompressible fluids and gases of fluid motion. In 1845 he published The Friction of Fluids in Motion and the Equilibrium and Motion of Elastic Solids. His many discoveries put the science of fluid mechanics on a new footing and explained many natural phenomena. Here you can see the Navier-Stokes equation. This is used to describe the flow of incompressible fluids. On the left-hand side, we have the mass, the density of the fluid, the acceleration, how velocity experienced by a particle changes with time, which includes the change in velocity over time, the speed and the direction in which the fluid is moving. On the right-hand side, that equates to the force, all the forces that are acting on the fluid, which includes the internal pressure gradient, the external forces, and the internal stress forces. Osborne Reynolds was an innovator in the understanding of fluid dynamics. He spent his entire career at what is now the University of Manchester. However, he did spend a short period of time working as a civil engineer in London, particularly in Croydon, working on the sewage network. His studies of heat transfer between solids and fluids brought improvements in boiler and condenser design. Reynolds most famously studied the conditions in which the flow of fluid in pipes transitioned from laminar to turbulent flow. In 1883, Reynolds demonstrated the transition of turbulent flow in a classic experiment in which he examined the behaviour of water flow under different flow rates using a small jet of dyed water introduced into the centre of a flow in a larger pipe. Here you can see a sketch of the experimental apparatus that Reynolds used. You can see the dye vessel and the pipe with a valve on it that then injects the dye into the main stream of flow. And on the right hand side you can see three sketches which show laminar flow at the top, turbulent flow, and then turbulent flow observed with an electric spark or a light behind it. So looking more closely at Reynolds' experiment, when the velocity was low, the dyed layer remained distinct through the entire length of the large tube. When the velocity was increased, the layer broke up at a given point and diffused throughout the fluid through its cross-section. The point at which this happened was the transition point from laminar to turbulent flow, and from these experiments came the dimensionless Reynolds number for dynamic similarity, the ratio of internal forces to viscous forces. Prantl was a German engineer who pioneered the development of rigorous systematic mathematical analyses which he used for underlying the science of aerodynamics. His father was a professor of engineering, and he encouraged him to observe nature and think about his observations. In 1901, he became a professor of fluid mechanics at the Technical University of Hanover, now the University of Hanover. His most important work was published in 1904. Now, I'm not going to try and pronounce that in German, but the translation is on the motion of fluids in very little friction. He described the boundary layer and its importance for drag and streamlining. He also described flow separation and explained the concept of stall for the first time, and this is an aeronautical term. So Geoffrey Ingram Taylor, no relation I might add, was a British physicist and mathematician, a major figure in fluid dynamics and wave theory. As a child, he was fascinated by the Royal Institution Christmas lectures, just as I was as a young child. If you've never watched one of these, make sure you tune in and watch them. They are absolutely fascinating and expose you to the world of science, chemistry, physics in a way that anybody can engage with, including young children. He read physics and mathematics at Trinity College, Cambridge. His work on turbulence in the atmosphere led to the publication of Turbulent Motions in Fluids, which won the Adams Prize in 1915. During World War II, he applied his expertise to the propagation of blast waves. He also worked on the Manhattan Project at Los Alamos, which led to the development of the first nuclear bomb. So in this slide, what I've done is create a summary timeline, which shows who was alive when, the work they did, and in some cases how that work then developed into future work undertaken by other academics and engineers. Spend some time looking at some of these engineers. Research who they were, where they worked, what they produced. Try and find some of the original papers that you'll be able to find either in the library or on the internet. And if you do find some of these original papers, please share them on the Moodle page so the rest of the class can have a look. So at the end of the lectures, I'm going to pose a question. And in this case, what I want you to do is go off and have a think about who made the most significant contribution to the subject of fluid mechanics. It's a difficult question to answer. And what I really want you to do is go off and investigate somebody who's made a significant contribution to the subject. I want you to undertake some library research. I want you to look at the reading list. And I want you to use the internet and other resources you can get access to undertake some research concerning a person who's contributed to this subject. Once you've done that, post your discussion and your opinions on the forum. So that's the end of the lecture. What we're going to look at in the next topic is fluid characteristics. We're going to examine the units we're going to use. We're going to look at density, specific gravity, and viscosity. Thanks for listening, and I'll see you next week.